So I just want to see that you've done some unit work, you've done some equations on there, neutral gaseous. I'm sure you guys know the equations now by heart. All right, and back to me. All right, so I am intentionally putting you in groups because I think, and this is some of the research I've done with grad school work, social learning in social groups where you have a chance to practice the language, ask quick questions, and support each other is more effective than just me being your sole provider of information, right? You've probably learned that through just school in general. So as we kind of rove through the day, I'm going to say, okay, to you guys need to chat in groups. That's why I have you kind of lumped into threes or fours. And then if I say back to me, then you guys stop talking, come back to me, okay? And it's going to be helpful for you to have both sides of the interactions today. So you saw a couple of things from your warm-up today. What do you notice I kind of embedded in the periodic table? What are you noticing? Just shout out anything you notice. So block, so S block, D block, P block, and F block. What else do you notice?
The numbers of the things.
What do you notice that's different though between these numbers?
They all start in different.
They seem to follow the electron.
This is actually related to orbital notation, which is the electron configurations we're going to get into in about 10 minutes today. But I see like 1s, and I see it over there as well, but that's just because of the location. I see 2s, and then I see, that way I see 2p, and then I see 3s, and I see 4s. 4p, but then this weird 3 in the middle, 4 on both sides of 3 in the middle. We're going to get to the reasoning behind that shortly. Okay, so let's scratch the electron configuration for a moment. We're going to jump back. How about problem set 5? Some things that you need some clarification on, some questions that I can work through. I'm ready when you are. Problem set 5. 6, like this 6?
Yeah.
Okay, so quick note to self. This is what I was explaining right before we ran out yesterday. The chart on the bottom, this is related, this transition is related to the last column over here. So if I look at an electron transitioning from 6 to 2, energy level 6 to energy level 2, is energy absorbed or released? Released. So you're automatically looking at the transition and writing down absorbed or released over here. And then if I'm working with this example like here, this 1, 2, 3, the third example here, and I have the only given, you see that little upside down broom, what's it supposed to look like? Wavelength. If I give you wavelength, I can't go and solve for energy. There's no association between energy and wavelength. There's no equation. What do I have to solve for first from that information? Frequency using what equation?
So C equals wavelength times frequency.
Right, so speed of light is equal to wavelength times frequency. You with me, guys? Yeah? Yeah.
Can you just like do one
One of the boxes?
yeah.
Let me do this one I'm working on and I'll go back to number 6, okay?
Right.
So 4.1 times 10 to the negative 7. 4.1 times 10 to the negative 7. Okay, so I'm doing the third example in the box. So if you have not done it, you need to do it with me. If not, you need to check your work. So what did it say? Wavelength was 4.10 times 10 to the negative 7th meters. Okay, so I know that wavelength's only going to appear in one equation. And that was C is equal to wavelength times frequency. I want to solve for which variable here? Frequency, which is V. C is a constant at 3.00 times 10 to the 8th, so we don't need to solve for that. It's a constant. So how do I rearrange this equation to isolate V? Divide by wavelength on both sides. Okay, so wavelength cancels on this side. So V essentially frequency is equal to C over wavelength. So, okay. So C is what? meters per second, okay? Wavelength in this example here, this was number 3 in the chart. So that's 4.0 or 4.10 times 10 to the negative 7th meters. Automatically, what units should cancel? Meters. Elijah, if it's better, sit on that side so you can look straight. I know I've got 2 of you guys in awkward positions. If you have some room here or behind you, can sit there, okay? I don't want you guys crane your neck and get a cramp. Okay, I need you the whole day. All right, so meters and meters cancel. What unit remains?
Per second.
Per second. Look at that, using your hertz or per second language. All right, so we know that remains. In your calculator right now, type this in. No options at all. I had somebody write me a note on the test. Where is the power, or where's the exponent on my calculator? If we practice in class like we should be, that shouldn't be a question. That shouldn't be a barrier to success. How to use a flipping calculator. So make sure you're working here.
7.20.
Give everyone 1 second to get that in your calculator.
Yes.
Now, I very thoroughly I like the engagement, like getting responses. It helps move the class along versus me waiting and twiddling my thumbs. So I would put parentheses 3.0 times 10 to the 8, parentheses divided by parentheses on the denominator as well. Is there a calculator? Does anybody need one? You guys got access, okay. All right, Natalie. What'd you get for frequency?
7.30 times 10 to the
14th what?
That's S-1.
Okay, so
Per second.
per second, or s to the negative 1. Anybody else get 7.30 times 10 to the 14th? You missed a zero someplace. Because I got this too, yeah.
I think like round it. Do you round it?
Oh, so when I put it in, I actually got 7.32. So if anything, I would actually put a 2 here, but I was looking for exponent really to make sure it was good. Something like that. There are 3 sig figs here and here, so there should be 3 sig figs like that, yeah.
After that, you just plug it in to get with the normal equation to get energy.
Yes, so that's our next step. So we've done that first equation. We've solved for frequency. So we have frequency. We already had a wavelength given to us in that chart. The last value to find in the chart is energy. So now we're going to take the information we have and solve for energy. What is energy's equation?
H times frequency.
H times V, right? H times the frequency. So energy doesn't have anything to do with wavelength except they are correlated. But what's the H constant?
6.626
Negative 34. Once you joules times seconds, right? Times second. So once you've written this up down about 5 times, you're like, okay, I could get this, like, this constant's tattooed in my brain. Like, I'm never going to forget it. But you have to practice enough to be very comfortable with it so you can expedite your process of problem solving. So that frequency we just calculated, which is V, right there, we're just going to plug it in here. 7.32 times 10 to the 14th. And I'm going to write that as per second as a fraction in this case. So you should see what units cancel. Seconds cancel, giving us a unit of energy, which is joules. So when you solve that now, what do you get for your energy?
4.84 times
10 to the negative what?
19.
Sounds good, yeah. So I can usually get a guesstimate and hear your answers and know if you're on the right track or not if you're putting your calculator. You can't really mess this up unless you somehow miss the negative on the experiment. So that's usually a fail-safe way. Okay, so this should be your energy, 4.85 times 10 to the negative 19 joules. So 2 equations over and over and over. But that's why seeing it Friday, seeing it yesterday through examples in lab, seeing it through problem set, I'm hoping that this sticks with you. This is one of the harder parts of this unit, I feel. Okay, and then I'm supposed to give some guidance number 6 now going back. So you'll do the very similar process. Now, I know you're looking at that and you're like, Jesus, it's a lot of work. If you do that once, twice, and okay, I've got the hang of it, abbreviate your work some. If you want to rearrange your equation and then throw your values in, or go straight to throwing your values in, you can abbreviate some, but I just need to see some juice. I need to see some of this versus just answers, because the answers are on your paper. Speaking of, I'll go back to 6 in a second. On the bottom of the paper, the answers are kind of mixed because I fit all the problems and the problem set answers on the same paper. So this should be aligned. If you want to take a picture of that, or I can put it back up there tomorrow, you'll know if you're on the right track because all the energies are generally like times 10 to the negative 18th or 19th. All the frequencies are about, in the 13th, 14th, 15th exponent. All the wavelengths are about in the negative 6th, negative 7th exponent. So I think you'll be able to match up some answers. It just may not be correlated. Okay? I'm videoing too, so you guys can check it there. Okay, number 6 was... I've been doing it for a while. 6, calculate the frequency of an X-ray having a wavelength of 2.5 times 10 to the 4th nanometers. Ooh, nanometers, that's where we want to do this one. Okay, so nanometers, 2.5 times 10 to the 4th. 2.5 times 10 to the 4th. 2.5 times 10 to the 4th. Okay. Nanometers, right? Okay, can I plug this right? Oh, sorry, pause. What was the question asking for? Say it again? Frequency, this is number 6, okay? What is the variable of frequency? The variable, what's the symbol? V, okay. So we're looking for V. So is there a relationship between lambda and V?
Meters.
Okay, so meters, yeah, so we need to get that convenience to meters first. So I'm hoping you're thinking of this equation first. You know you're solving with this equation, except you know that many times this is in meters and this is in per second, which correlates with the meters per second that the C value has. So yes, you're right. This nanometers is not going to work for us. Let's go ahead and convert. So 2.5 times 10 to the 4th nanometers, multiply by doing your dimensional analysis. What do you want to convert to? Meters. So no meter needs to go on top, and I know the nanometer needs to get canceled down here. What's the relationship? Who gets 10 to the 9? Nano, right? There's one huge meter with a billion nanometers in it. That's going to allow us to convert to meters, which we then could plug into the equation. So I think I'm just going to stop here. That's okay. So that's 2.5 times 10 to the negative 5th meters. And that's the lambda. That's the wavelength you would truly plug in here. Give me a thumbs up if you're feeling okay with light. Feeling okay. All right, so still got some people I'm gonna work with maybe this afternoon, but if you or this after the first part of it today, yeah.
Can you explain numbers?
So that's why you guys did your lab yesterday, so that you would feel comfortable with this. So 10 has a light measurement of 3.5 in the spectroscope. In the spectroscope, what did you guys have to do to get that to actually angstroms? Multiply by 1,000, so 3.5 in the spectroscope meant 3,500 angstroms. What was the conversion between meters and angstroms? 1 times 10 to the 10th what? What do you say? Angstrom. Angstrom. Heck, no, that's like 10 billion meters in angstrom. Think about light. We're the opposite. So you could say 1 times 10 to the 10th. Little bitty teeny tiny angstroms in 1 huge meter. That will be your relationship there. And then from there you guys will finally convert and move forward. Alright, so keep reviewing that. But if you didn't do much on light last night, 1, you probably don't have educated questions to be able to ask me, and 2, you got a night ahead of you, people. Okay? So my goal is to let you start finishing some of this at the end of class. But we're going to talk about electron configurations. But remember, I was telling you about the little collaborative dialogue stuff we were going to work with. I know you're in high school, and I know you think you know how to work with peers, but I found it to be really very helpful for us to be on the same playing field. I need about 5 minutes of open-mindedness and working with me on yes and. All right, so let me tell you the logic here. Some of you guys are really advanced. Some of you guys don't need my help. Some of you guys don't need each other's help. But you have something to contribute to the group, right? So it's kind of like just being a good person to talk with you. So if you have something to contribute to the group, you should want to empower people to kind of give back, have a role to play, have some conversation pieces they can add to the conversation. So how do you say that without saying, I really want all of you to equally participate in the group? Because then they're like, okay, Emma, we'll do that. So it's just about your conversation, about how you're going to talk to each other. So I could easily say, I love chemistry. And Carrie could go, yeah, but not all of us do. See how she just kind of just threw me under the bus? That's not good for conversation. So instead, Carrie could say, Yes. And we also like our English class and our other math class. So sometimes we need to balance our lives. So she furthered my thought, but then gave me some more perspective. You see how I did that? Okay. So we're gonna practice that instead of doing yes, but how that's got that negative annotation to it. We're gonna say yes, and Kendall, I think we should work together on this project. Or yeah, but I don't know if I want to work with Kendall. So just kind of how you just body language, how do you interact. So that's the kind of the background. We're gonna stop on that for a second. Take a second, read this. We're gonna do anding in a second. Read that first. Alright, so Justin came up. You guys move up to this little area with Zach's group, and then you guys from his group move over to Austin. Because that's more people there. Okay? So, as an example of this, we're going to do just a silly conversation. You can come to the group, so stand up everybody, get to the group where the told you. And as an example of how this can be used anywhere, especially in science. If you have a strong opinion on something, you can come across as pretty harsh and just not open-minded, right? So I can say, guys, I think business is the best element out there. How would you respond?
Yes.
Okay.
And carbon is great.
Okay, so you can come back with something. So come across with whatever standpoint you want to. It doesn't have to be chemistry related, but I want everybody to yes and it. Yes and, yes and. Go. So you guys want
I think that intervention is the dumbest thing I've I think that intervention is the dumbest thing. Yes,
I think we got it.
I'm coming.
No, I meant to question before that.
I think I'm gonna get real busy. That's a problem.
Positive guy. Yes, and AIDS. Yes, and AIDS. And I keep on that one.
We're not wrong.
Yes, and I haven't been to Raleigh since fourth grade. Yes, and I totally agree.
I totally agree with that statement.
Yes.
We're not coming up with
It helps give you perspective.
I think school is however more I think that is
However, in the library, I think it's.
I haven't even
you just call it.
You see how I ended that?
Yes, and that's a great idea.
And encouraging positive thought is a nice one. Alright, so we can.
And I think what are we talking
What's our, what was the initial,
Teal time, like talking about interventions. We're talking about it. Some people don't like it. Yeah.
so what was the start though?
Well, the start was, Kendall said she didn't like intervention, and then Jessica said that she agrees with her, kind of like agreed with her. And then Carrie brought up that she liked the old Teal time, and then we agreed with her.
But then I said I think school because
we found something.
Oh, okay.
Mine was a false statement, but
But we needed some standing practice. Okay. So what was the first period becoming?
I'm doing all the right.
that, you know how like they let us like have like
Yeah, I'm trying to
dominate teams remember your system in your class. And Doc was walking down the hallway with our teacher standing right outside. And goes, "Hey, clean it out, thanks a lot." And he turned around and started walking the other side.
Yes.
You know, something
They don't
happened.
do it because you know the reason they do
I almost thought I was supposed to study at 4.
You're like, that's wait.
Apparently, if you get like 3 right up, so you can just come in for the then you get 11. And I got 5 this week.
I got 5, right?
Okay,
It's only Monday.
And then I had
so we're gonna talk about life. And back to your seat, back to your seat. Let's talk about life decisions.
No, he got rated up at Liberty.
All right, so to maintain that activity, I need, let's say, there's not quite 20 of us yet here. So I want you guys to make an atom, only the electrons with your bodies, people atom. Ignore the nucleus. The nucleus is just chilling there in the middle. Of the biggest element you can make. You have a minute. Go.
Oh, and the whole class?
Everybody is equal. Everybody is equal.
Are we just spitting electrons?
Like the first level can only have 1 electron. No, the next one's 2. You had to bring up electrons. This is low.
Seriously? That's the electric.
So the first order only has 1. Right?
I need everybody involved. Jack, get up. So, Chris, this time, yes, Chris is trying to help organize too.
All right, Chris.
Okay, so
Well, we don't have everybody, so that we can.
Chris,
that's 30 seconds.
Chris, possible.
Okay, so hold on, do the inside, so I'll start the second show.
Outside.
7, 8.
All right. It's outside show, get out there with Matt. I mean, not Matt, Joe, sorry.
We're going to be an outside.
Alright, hands, 3, 2, and 3. Freeze. That means you're not talking. So I've got 2 in the first energy level. Raise your hands. 2 in the first energy. 2 electrons, okay? And then second energy level, what do we have? 1, 2, 3, 4, 5, 6, 7, 8. Who knows this information from like middle school or physical science? Okay. Or just in general. So there is a pattern, right? The last or the third energy level can hold up to what? 18. Actually hold up to 18. How many do we have up here? 1, 2, 3, 4, 5, 6, 7. Okay, so we can have some more space, but we definitely have 7 up here. How many electrons total do we have? 17. Who are we? 9, 2, Chlorine. Okay, so pause. So you know there's a method to the madness. You know that there are electrons that fulfill these outer energy levels and kind of build to make huge atoms. So like iodine has how many electrons? I can't see that. 53. So we have more and more shells. Okay, but there was an arrangement. This is called an electron configuration. The configuration of where the electrons exist in the atom. Now, that's like baby right there. 2, 8, 18, that's just memorization of how many electrons exist in an energy level in a shell. We're going to talk about it in a little bit more depth. Back at our seats, let's go. Thank you.
32.
We don't do it based on memorization, we do it off knowledge. Okay? Kind of, but it's still memorization. Okay? All right, you have 3 seconds to get back to your seats. Let's go. I have quite a number of problems to do here. Because I want to make sure you are supported for homework. All right, so as a Alright, so that was an activity to kind of let you see that you know a little bit about this already. You know that there are electrons that live around the nucleus and these big electron clouds, and there's a system, there's a pattern. The pattern we're going to speak of actually will use letters S, P, D, and F, which is what you wrote down for warm-up, right? But to give you some context, let's talk about the history really briefly. It's the quantum mechanical model notes. I printed this for you in the back side of your isotope notes. Back side of that has like a little blurb 1 through 4. I'm going to add to that first, and then we'll kind of get into what the actual electron configuration written work would be for. Okay. So who's Bohr in my scientist groups? Who's Bohr? Okay. So I got 1 Bohr, 2 Bohr. So you guys, I don't know if you knew this. Listen up. Bohr has this great model called the Bohr model, but looks like your blue sheet in front of you. What does it describe? Bohr model of hydrogen. It is only applicable for hydrogen. It doesn't work for anything else. The way that he described it, it just doesn't happen in nature. So yeah, it's great for hydrogen, but it doesn't work for the rest of them? No. So then we had to kind of develop another theory or another way to explore and explain the rest of the atoms in the world. So quantum mechanics came about with Schrodinger. Who's Schrodinger in my groups? Anybody? Okay. Schrodinger, de Broglie, Heisenberg, Einstein. Gosh, a bunch of scientists came together and helped develop this new theory called the quantum mechanical model. Doesn't that just sound complex? The quantum mechanical model. It does sound cool. So we're going to only dive into it a little bit because it's like theoretical physics. It's pretty far up there on the pay scale, but we're going to talk about the basics that we can. So quantum mechanical model, we're jumping in. So the first thing to note is this part down here, past the green, is what's on your notes. So if you want to jot down some of the extra stuff, it's up here. The way Bohr described the location where electrons can exist, he called them orbits. Okay, and an orbit had a set pathway. The set path was exactly what you see on the little blue sheet with the Bohr model, those concentric rings. Well, Schrodinger and his friends said, okay, yeah, you're right, electrons have energy. They have a set amount of energy, which is what this word quantized means. I think I have it down here, maybe I didn't, okay. So it has a set amount of energy. He said, yes, Bohr, we agree with you. They have a set amount of energy that they can kind of just naturally have. But they don't move in set paths. He said they move in orbitals. So Schrodinger's quantum mechanical model doesn't say they have a set path or orbit. Instead, they are free to move around the nucleus in electron clouds. So you guys kind of formed those clouds of your body. You formed a small cloud, then you formed a medium cloud, and then we formed that really big cloud, but only 7 of us were in there. So we know those exist. But there's a little bit more than just a cloud there. There's actually orbitals. There's some specific locations that the electrons live in. So that's what we're going to describe. So these clouds, they have shapes. So these shapes you'll want to draw. So S is the name of one of the orbital shapes, and S stands for sphere. So there's one that just looks like a sphere. Pretty easy. Then there's another type of shape that the cloud can look like, or the orbital can look like, and it's called P. It's a dumbbell. It's like an up and down dumbbell. But a sphere, think of it like a 3D shaped sphere, and think of like the X, Y, and Z axis. Can you reorient that sphere in a different way? Yeah. Does it change? No. Okay. So there's only one version of the S orbital, because it's a sphere. You can't make it look different. It's a sphere. But this P, which is up and down, what axis is this? Y axis. What else can I do with that? Turn it to the X axis, okay? Or turn it to the Z axis. So it's like in the board and then out of the board. It's supposed to look 3D. Look at my artistic skills. Okay. So P and P. So there are how many different orientations this can take? 3 different orbitals is what we call that. There's only one orbital in S because you can't turn a sphere any other way. P can take on 3 different orientations. There are 3 different orbitals it can take on. Okay, what's the next letter?
D.
D. So D orbitals, they have a double dumbbell. Dumbbells right here. It's like 1 and then 2. Double dumbbell, like that.
Oh, it's one of those clover intersections.
Yeah, it's like a clover. Perfect. So S is a sphere, P is a single dumbbell, D is a double dumbbell. How many different orientations can this take? This is like X, Y, X, Y, X, Z, Z, Y, and then there's this like weird diagonal one, and then there's one with an inner 2 on it.
11.
Okay, 5. It has 5 orbitals. So this times 5 orbitals. That's the D orbital. What do you see is happening as I go? S has 1 orbital. Thank you. T has 3 orbitals. D has 5 different shapes or orientations it can take on. So how about the next letter?
E has 7.
No. Look at your warm-up. F. Thank you. So S, P, D, F. Those are the 4 letters we will use. That's why I wanted to prompt you earlier with that information. F has a, I'm going to draw it down here, has a kind of a flower shape to it. So it's got like boom, boom, yeah, look at that. Okay, so it's just a flower. But there are 7 different orbitals or shapes that can take on. Basically, an orbital is just a location where the electron lives. So it can either live in something like a sphere, a funky little dumbbell, or a double dumbbell, or a flower. It just gets more complex as you go. I'll show you what these actually look like though. So here's the s orbital, it's just a sphere. P individually, and then when they're all laid on top of each other, they look like an overlaid 3 dumbbell system. Here's all the different orientations that the double dumbbells can take on. There's the inner tube thing I was telling you about, just weird, just how it is. And then these look like pacifiers, balloons. So, but how many do you see here? 7, and those are the 7 orientations the F orbitals can take on. They're all just big bubbles, but I just want you to know that there's a number associated with them, like how many you can take on. So you can imagine if I layered all of these on top of each other, all of them, it would just look like one big blob, right? Yeah. That's what we draw atoms as circles, blobs. This is because nobody's got time to be drawing these orbitals like this. So I just want you to know that they exist, but we're not going to draw them all the time. You should know the sphere, dumbbell, double dumbbell, and flower, the kind of name that we give those shapes. All right? So that's kind of what Einstein and Schrödinger, they said that these electrons exist in a cloud that look like those shapes. So sometimes we have to describe information about the orbital, like where is it at? How big is it? How many electrons can fit in it? So these are the descriptors of those. So the first descriptor is called the quantum principal quantum number. We label it N. Where have you seen N before? N equals. Right. When you're looking at your energy levels, look at your reference table. You have that Bohr model. Say again. Oh, no. So you guys saw these like N equals on your Bohr model, where we were describing it as the energy level. So that's old news. You know that N means the energy level that element or that electron exists in. But you can probably think about it. If I have an energy level 1, it's really small, right? Energy level 1. If I have energy level 2, comparatively, it's what? Bigger. Energy level 3, bigger. So it just tells you the relative distance that electron is from the nucleus. So far, so good? Okay. Then you have the sublevels. It's called the angular momentum quantum number, but that's just the name of it. It tells you the shape orbital you're dealing with, S, P, D, or F. So S, P, D, or F, there we go. We know about those now, but it just gives us a description of what we're talking about. Then, occasionally we have to say, oh, it's the p orbital that's up and down, or it's the p orbital that's in and out, or sideways. Sometimes we have to narrow in on the orientation of the orbital, but it's not frequent that we have to do that, but we just have to know that there are orientations that exist there. So this is like a definite. We will talk about the level. This is a definite. We will talk about the shape. Not so much. We won't really talk about that, except just as awareness. And the last thing is, we're talking about electrons, right? 2 electrons, if they get together, let's say this orbital looks like this. Do you think that this electron and this electron want to be near each other or far away? Why? Yeah, negative to negative, that's going to cause repulsion. Okay, so if it's going to repel, we're going to have some really unstable atoms here. And then, atoms won't be able to exist, and they might cause some corrosion or react. So if we want them to remain stable, we give them an option. Either you can spin clockwise, or you can spin counterclockwise. But when they spin in opposite directions, it allows for them to get rid of some of that repulsion. So we try to say one spinning up and one spinning down. But when I say spinning up, I mean clockwise, and if I say down, I mean counterclockwise. It's just how they spin so that they can kind of limit some of their built-up energy. Yeah.
So on the PS5, it says going on this job level diagram.
We're gonna get to that in just 1 second. Yeah. Don't even touch it yet, because I don't want you to draw it like this is middle school when we drew it like this with dots. Big fat lie. That's only for bore. I mean, only for hydrogen. We're gonna learn how to draw that in just a second. Good question. Yeah.
So as far as those orbitals go, like where you're talking about the ones for hydrogen, how they're like far apart and like get close together, is that because like the electrons in each shell are repelling each other?
It has something to do with that and the attraction to the nucleus. There's a balance between repulsion with the electrons and attraction to its nucleus because it's positive.
And then it gets more attractive like is it farther closer?
It actually is as it's closer. That's why the first energy level is so close in, and then the second one's farther. It's called shielding. We'll get to it. You have some good questions. Thank you, guys. Okay, so that's it for like the quantum background. But those numbers and letters we're going to use right now. Okay. So everybody find oxygen. Periodic table. Find oxygen. All right. So what atomic number is it? 8. I should see everybody looking at a periodic table. All right. So atomic number 8. So it's like right here. All right. So it's going to take some building of this element to get to the final electron count that oxygen has. How many electrons does oxygen have? 8, because it's atomic number 8, aka protons are 8 as well, right? So we have 8 electrons to build from the inside core to the outside. So the way it works is I like to use the periodic table because it gives us a guide, and if you understand how to do it, I'm not going to always give you this SPDF thing here, but you'll notice is that the first block is S block. And then I told you guys on warm-up that one helium one, it was pink and it said 1s, right? It actually belongs, helium is very similar to hydrogen, so it belongs right there next to hydrogen. We have it in the noble gas group simply because it acts like a noble gas, so it was more relevant for behavior to be there. So as you build an atom, you have to start with the first energy level. So this 1 here means first energy level. You wouldn't start in the middle of the atom cloud and say, I think I'm going to throw an electron there, right? You're going to start from the inside and move out. The letter there, S, means that I'm dropping an electron in the S orbital. So I'm going to say 1s. I'm trying to write out the electron configuration. I'm going to only get over here in a second. How many electrons can I account for right here? 2. 1, 2. Because every time I move forward in the periodic table, am I not adding a proton? Right? I'm adding to the atomic number, hence I'm adding a proton, hence I'm adding an electron. That's why I'm counting 1, 2. Have I exhausted 1s? I know this one's over here, but I moved that over there, right? Have I exhausted 1s? Yes, so I have 1s, 2. That exponent there means I have 2 electrons in the first energy level in the s orbital. First energy level, s orbital. Now, I have surpassed this. I'm done here. Done. Moving on down, just like you're reading a book. Now I'm in the second energy level. But I'm in the second energy level, but I'm still not the P block. I'm at S. But how many electrons or how many elements am I moving through? 2. Okay, so 1, 2. So that's 2s, 2. Now I'm moving across the periodic table, and now I'm in P block, right? What energy level? What energy level? Still in the second period, meaning I'm still in the second energy level. So 2p, because I'm in P area. How many electrons over do I have to go? 4. 1, 2, 3, 4. Sorry, we're stopping oxygen. That was my example. So this is oxygen. Okay, so I'm stopping here at oxygen. And I don't go all the way through, so I counted 4, I write 4. Okay? How many electrons are total in oxygen? 8. How many electrons total do I have here? Count the exponents. 2, 4, 8. Okay? So that's step 1. Then understand, you guys who are building the inner core, I think it was Austin, who was in the middle? Andrew? You guys were my 2 electrons in the middle. You guys were 1s2. Who was in the 8 on the outside? Or in the middle, right? So 6 of you were needed to make oxygen. If I had to let all 8 of you in, I would have gone to 6, which meant I would be who? I would be 2 forward. I would be neon, because that's a different element. It has a different number of electrons. And then last group was, I think, 7 on the outside. So I would have gone 7 more. 1, 2, 3, 4, 5, 6, 7. Who is this? Who were we? We were chlorine. So the elements build up their energy level shells with electrons based on how many electrons they have. And there's a method: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and so forth. It's a pattern. So let's backtrack. That's an electron configuration right there. That right there. But what do the numbers mean? Here's what everything means. 1, that first coefficient-like number, that just means the energy level we're talking about. You might want to write down this like legend because it helps you understand what the numbers and letters mean. So that number in the front just means I'm the first energy level. I'm the first period. And on a periodic table, where is the period located? Horizontal or vertical? Horizontal. Okay, so that's a row. The letter is just telling you the type of orbital, S, P, D, or F. It gives you some indication of the shape and how many different orbitals I could have. And then the exponent is the number of electrons in that orbital. What's up, Andrew?
Wait, back on the slide that we had for one
Mm-hmm.
period, the numbers will change.
Only in D block. We're going to get to that in a second. Most of the time, the period number is the energy level. That one exception is when you hit D block, which is the middle transitional group in the F block. Okay. So this is kind of the description, the legend behind it. Let's go back to oxygen. What was the electron configuration of oxygen? 1 S2, 2 S2. Are you following on your periodic table? 2p4. Okay, that's the electron configuration. Now, a configuration is just a bunch of letters and numbers together. The orbital diagram, as Andrew was leading us to, a diagram is usually a picture, right? Okay, an orbital diagram is going to show this in a picture form. Basically, we draw orbitals, instead of drawing them with these funky shapes, because that just takes so much time, we draw them as dashes. So if I put a dash, and I put 1s under it, I'm saying that's the 1s orbital. How many electrons are in my 1s orbital? 2. How do electrons behave in the orbitals? They spin up and down. They spin clockwise and counterclockwise. I'm going to draw it as an upward arrow and a downward arrow. You're doing this with me, right? Because I'm only going to do a couple really good examples, elaborating, and then you guys are going to practice. All right, so that's the first energy level, first orbital, 2 electrons. Then I have the second energy level to work with, but I have to draw the orbitals separately. I label it 2s. How many electrons are in 2s? Up and down, 2 electrons. Then, here's where it gets funky. How many orbitals are in the p sublevel?
3, so you do F1.
Yes, and you actually don't have to label them X, Y, and Z, but that's your awareness. You know there's a background. You know the background here now. But we're drawing 3 dashes. That's how we're labeling it. 1, 2, 3. And then put a little bracket there to say all of these together are the 2p sublevel with 3 orbitals in it. Hear that vocabulary? 2p sublevel, 3 orbitals in it. And I didn't already say the magic rule, but have you figured out what the magic rule for number of electrons per orbital maximum? How many electrons can fit in one orbital? 2. That's why I didn't add more there, right? So maximum I could put 2, 2, 2, right? I don't need all that space though. I only have how many electrons? 4. So here's the rules. Did you guys, do you remember doing on your reading guide 5, which I'll pass back if I can today? Hund's rule, Pauli exclusion principle, and off-ball principle. Do you remember that at all? Okay, so let's go here. 3 rules that govern electron configurations. Write those down. I'll tell you how to memorize them. I was also a 10th grader having a hard time memorizing the rules of chemistry. So off-ball, that just means awfully low. I start putting electrons awfully low is how I remember it. Off-ball, awfully low. You start putting electrons in the lowest energy level. What energy level is that? 1. Did we start any place other than 1? No. You're like, duh, we start at 1. Start at first energy level. And then you go to the second, and then you go to the third, and then you go to the fourth. That's kind of like a duh rule, okay? Then, Poly said you can only pair them up. Poly pair, poly pair. You can't put 3, 4, 5, 6 electrons in a little bitty orbital. You can only put 2 maximum. Question? Okay. And that orbital I'm labeling as a line for us here. And then I remember this one. This is the golden rule, okay? Hund's ones rule. My AP students still say this. We're doing this like right now in AP. Hund's ones rule. If you have an option and you don't have to fill up an orbital because you've got space in the whole entire subshell, electrons are negative, right? Electrons and electrons do not want to be next to each other unless they absolutely have to live together. So I'm going to demonstrate that now. You put one electron in an orbital at a time. And then you have to go back and fill it up, you will. But you only fill it up to a pair. No triplets and quadruplets. Thumbs up when you're good here. I'm going to stop after this example, give you a breather here. Okay, so continuing that oxygen example, I'll go back if I need to, I promise. We kind of got the 1s, we got the 2s, 2p. I have 4 electrons. How do I put them in here? According to the rules.
2 in the first one.
Whose rule are you using? So we've already been using off-ball because we put it in the first one, and then we put it in the second one, and then we put it in the third one. We've been using off-balls this whole time. Holly says that's the maximum.
So,
Hund's ones rule. 1 at a time, and if you have to go back and refill, you will. So put 1 spinning up in the first orbital, 1 spinning up in the second orbital, 1 spinning up in the third orbital. How many electrons have I put in thus far?
3.
3. Do I have more orbitals?
Put it down.
I can put a down one here. So how will I know you don't follow the rules? Because you guys would have put 2 and 2.
Yeah.
And that's how I know if you're following the rules or not. Because the goal is electrons don't want to be near each other. 1, 1, 1, and then go, oh gosh, I got to put 1 more in here. You don't have any more orbitals to fill, so you have to backtrack. Does that make sense? Yeah, I want to start you off. I want to start you off with a simple one first.
Yeah. That doesn't make any sense.
Yeah, I'm getting there. I got 3. 3 I'm doing right now. Okay. So I'm going to have you guys do sodium. Find sodium. Do that now. Exact same process. So you guys are going to do sodium and chromium. Sodium and chromium at your tables. Go. Go back. Yeah. Let me just make sure everybody's good.
Sodium's 11.
Back to
This
the.
one's chromium.
So guys, negative talk doesn't help you at all. It just depresses you. Negative talk is not useful.
You said chromium also?
Yeah, sodium.
Yeah, alright.
Where did you get chemicals?
Is that what you argued?
Like the
Oh, I think
But so she did something where she like wanted counts and stuff. So we counted it because this is period 1. It's in the little S part and then you try it and come over it. So yeah, and then you go down and you're in this block. Right here. There's 200 yeah, I said over. And you're like, whoa. So I'm still in period 2. I'm still on the second row. But I'm in the key block. And then there's 1, 2, 3, 4, 5, 6. And we go down again. You still haven't gotten to and now we're going to period 3. And the other block, yeah.
you had like you're gonna follow it. One second. You're gonna follow it like you're reading a book across your table row by row.
Okay.
But you must know everything here is called S block. Everything here is called P block. Everything here is called D and F. So that's what's color coded. So when you're doing this, you're gonna go 1S, 2. Yeah, because you're an S block. And then when you get here, because we've already successfully gotten all the way across there. Carrie, what's up? Give you 1 second? Okay. Just make sure it wasn't urgent. So 1S2, because you're going across the first period, S block, 2 electrons over. Done. And then you're going to go to the second energy level, second, so in the second period, S block, 2 electrons over. So keep following, keep following, keep following. Now I'm in P block. So you're going to go 2, because I'm still in the second period, but to P, how many electrons over? I have to look at my picture. Mine's a little colored on. 6. So that's 1S. Oops. That's 1S2, 2S2, 2P what? 6. Okay, that gets me here. Then I'm going to go over here. Where's sodium at over here? Right here. So I'm in now what period? What period? What period? Periods are the rows. What row is this? 3, third period. And then I'm still in S, so you're right with S, but I'm only 1 electron into it. So I'm only going to go 3S1. That's the electron configuration for sodium. And then you'll look at all the pictures.
So how do you get 1S squared?
Because it depends on how many electrons or elements you move over throughout this periodic table. So like there's a helium field here. So that's 1, 2. 2. 1. Whatever. So that's why the examples.
How come we didn't go across on that second round? It's so
What's the up and down?
I did. I was just stepping before the 40. All right, guys. I want you to keep working with your groups for another minute.
What was the second one you
Chromium. Yes. You want to picture this? Okay. I'm gonna use the board. So first, I need the board. So take a picture now.
Yeah, can I have a picture of that too?
I'm gonna erase it. So if you want that now, take it. I didn't want it. Huh? I want to without the one. Okay. I got you. Now I actually got you. So I'll just wait. Because that's how P has 3 orientations on the board.
Oh wait, 4 D. Just go into the actual app. Like you
All right. I will come back to that. I'm not erasing it. And back to me. And back to me.
I'd say my camera was like.
Oh, I'm not erasing it. It's fine. Sodium, and then we're gonna go to chromium. Yeah. Okay. So let's start with sodium. I'm looking across the periodic table. Let's follow along. 1S. What? 1S2. Then what else? 2S2. Where am I at right now? What element? Currently I'm at beryllium. You with me?
Yes.
That means you should be looking at your periodic table. Okay. After that, you fulfill all the way through P block. So what is that? 2P6. Stop. Who am I at? Neon. Okay. I'm currently at neon. And then jump down to the next level. 3S1. And that's stopping halfway through S block because I told you stop at sodium. Okay. And if I said 3S2, you would be at who? Magnesium. Okay. So from this information, draw your orbital diagram. 1 dash, 1S. 2, 1 up, 1 down. Next, 2S, 2. You're simply following your guide. Then you got 2P6. How many orbitals do you have to draw for P block? You have to draw 3. And then you label them all 2P.
They're all 1 up, 1 down.
Awesome. So they're all 1 up, 1 up, 1 up, and then
1 down.
1 down, 1 down, 1 down. Just respecting Hund's rule. Okay? I would never know if you didn't do that on that one because you're full there. Now, how do I draw this last one?
1 up, 3s.
3s labeled, 1 up, right? Off the bat, how many electrons does sodium have based on periodic table? 11 electrons. How many are, how many are here? 2, 4, 10, 11. How many are here? 11. Okay, we should have 11 across the board. Second point to make, there's this word, I think some of us know it. I want to see, what do you call the outside electrons? Valence. You had Miss Austin. I know you guys know it because she teaches the basics of chemistry. Covalent means co-share valence electrons. Look at you. Okay, so this guy right here, I'm change color here. Circle this, write this down. I'm expecting you will know what valence electrons are now, okay? Yeah, so valence electrons are in outside, actually I'll say highest energy level. EL means energy level. How do I know this is the outside or the highest energy level? What do you see that tells you that? It's not that it's the last one. That's what I was waiting for. It's the, what's the number you're seeing? 3. The 3 means energy level. The 3 means highest energy level. We're going to get into a situation in a second where the last one isn't the case. That's why I wanted you to say that, Chris. Thank you. Yeah. I'm getting there. Yep. I'm going to get to the next, maybe not to 117, but like 82. So I'm going to field questions in a second. Love you, but I have 20 minutes, and I want to make sure I get to your extra questions you're getting to. Chromium. Ready? 1s. Follow along. Chromium 1s2. 2s2.
2p6.
2p6.
3s2. 3p6.
Pause. Where am I at?
We're at after 3p6.
We're at argon right now, right?
Argon, yeah.
Okay. Notice we're always hitting the end of a block. Now next. 4s2.
44.
Hold on, Andrew. What did you say? Andrew? Thank you. Okay, it is 3. This is where I told you guys, and just listen. I love your commentary. I love engaging classes, but I want to make sure I'm answering your questions too. So this is where we had the break from S to P. The rule of thumb is when you enter D block, you take N minus 1. So that's why instead of saying 4, you say 3. But when you surpass the D block, you're going to move on to P and just do normal. If you're in the 4th row, you're in the 4th period. Similar rule with F block, if you get down here, which we'll get to, I hope by the end of class, is you'll do minus 2. The reason behind that is based on the energy levels themselves, and I'll show you why in a picture. If I have the picture closed, I'll get there. Yes, it's okay. So this guy right here, this is off-Ball's diagram. Off-Ball, awfully low, he says you fill the electrons from the lowest energy level to the highest. But they sometimes don't follow the sequence of 1, 2, 3, 4, 5. So it goes 1s2, 2s2, 2p, 3 orbitals. Oops. So there's 3 orbitals, so we can fit 6 in there total, 6 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then what? 3d. It's just a hair higher than 4s and a hair lower than 4p. You see it? And then 5s, and then 4d, and then 5p, 6s.
5d, 6p, 4f.
Sorry, I didn't get over there. And that's why, instead of making you memorize this crazy thing, I mean, what? No, you can't memorize that. I'm going to tell you the trick. When you hit D block, you minus 1. When you hit F block, you minus 2. Okay? That's the magic. Yeah.
Can you use this chart thingy?
You can. That's how my teacher, is that the diagonal? That's how my teacher taught it to me in 10th grade. I had no idea what an electron configuration is because all I did was memorize the diagonal chart. I didn't know what an electron configuration was until I started teaching chemistry. I just could memorize. I was like, yeah, I could follow a diagram. So you can use it for yourself, but I think this makes more conceptual sense. And that's why I teach it this way. Good question, because that's how my teacher taught it. I was like, oh yeah, I can memorize that chart. I can totally do this. Okay, so I'd rather you learn. Sorry, it's a curse. All right, so 4s2, 3d, thank you. Okay, orbital diagram, here we go. 1s2.
1s. Wait, okay.
2s.
Okay,
2s, up, down.
2p, up, down, up,
And you should be drawing these with me. Thank you. So one up, one up, one up, one down, one down, one down. Okay?
3S.
3S.
One up, one down.
3P.
One up, one up, one up, one down, one down, one down.
Okay.
4S, one up, one down.
Okay. How many orbitals are you drawing for 3D4?
You're drawing 3.
5. Thank you.
5.
I told
Yeah,
you
5.
the sequence: 1 orbital, 3 orbitals, 5 orbitals, 7 orbitals. Regardless, you will draw them all, even if you don't need them. It's just saying I have available orbitals. You feel free to drop some electrons in there. So for that 3D4 we're drawing right here, 1, 2, 3, 4, 5 orbitals. All of those orbitals are 3D. But how do I put my electrons in? Up, 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 up. Thank you. Those are half arrows. Sorry, I get a little lazy. Okay.
So you don't have to fill it.
No, that's the point. You fill it in one at a time according to Hun's one's rule. If you have to polypair them up, you have the ability to. Okay? So, one more for you. Lead. PB. Lead. 82.
What?
You can knock this out. You've seen the repetition. You got this.
Yeah, the only star storm you put on those around my neck and kick Oh, I'll kick yours, you kick mine.
Talk to your groups, guys. That's why you're in groups today. This 3S is this 3S.
Oh,
I'm just running out of space.
I thought like this 3S was like.
No. So this is this. This is this. This is this. All. This is way over here. Way over here. Alright. That's why I'm labeling it underneath because it's hard to keep it right on top of it. Good question. Yeah, thank you. Hey. Oh, hold on. Look at it. Right here.
Yeah, it's 6.
Keep talking to your groups, guys. Rex, I want you to start without me here. We just went through. Can you start this? We do one. Do this first. When you go to lead, no, we did 1, 2, and then over here. Yep. Go down. I hear you. Give me a second.
6.
Yeah.
So once you get to
6.
those throw you off the block.
Wait in circles. See what these are.
So I don't have enough. I didn't help again.
I'm at 6S too.
When you do 5D, do you count?
No, look, that's only. This is all of it.
I'm gonna do that right now.
To VA. I still have to do all of these and then all the way
Okay.
there.
All right, pause for me in your conversations.
please.
Come back to me. So, I'm expecting you're keeping up with my pace just a little bit because I want to make sure I hit quality examples and get as many questions as I can to you. Who got to 3D10? You got to zinc. So that's so repetitive, right? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That's the first time we've gotten to 3D10. Success. Pat yourself in the back. Then next is what? 4p6 because we're going all the way across p block to the 6 to the krypton. Then what's next? 5s2 and then that gets us all the way from the good. We drop down n-1. We drop down to energy level 4d10. And then 5p6. That gets us all the way from indium to xenon. 6s2. Okay, so the 6 is because we're in the 1, 2, 3, 4, 5, 6 period, right? So that's 6s2. Stop. Okay. I see a lot of us are good here, but it's only because your periodic table has a gap in it, those neon colored ones. So it's just this lanthanum and actinium, they actually live here. So I do hate that that one took it out. Listen, I hate that they took it out because it just gives you a little bit of misinformation. The lanthanum and actinium actually live there. They live in D block. But we're going to surpass all of them, so it doesn't matter. How many electrons should be in F block? 14. Who said it? 14. So it's 4F14 because how many orbitals are in F? We went 1, 3, 5, 7. How many electrons fit in an orbital? 2. So 7 times 2 is 14. So there should only be 14 across here. I know yours has 15. It's just because they took the lanthanum and dropped it. I don't know why. It's mainly because the periodic table shouldn't actually look like this. It should be really, really, really long. It should be about this long. So they do this to keep it in a textbook on a nice little 8.5 by 11. That's why they drop it down. But regardless, we're going to go ahead and fulfill the, you could say, go ahead and do, what are we at, 6? You could do 5D1 to account for lanthanum. And then you go 57 and 58. And what would you say this is? 4F. This is 4F, right? And that's 4F because you drop down to a second level, 14. That gets us all the way from 58 to lutetium, okay? Why is it? Because remember we said n-1 here, n-2 when you hit F block.
And then 5D9.
And then you could do 5D9 and that gets you to Mercury. But here's the thing at the end, guys. You got 5D1 and then you have 5D9. Wait. You got both of these separate. They shouldn't be referred separate. They should total to be 5D10. That's what I was saying. If you want to do it initially, if you're stopping halfway through D block, definitely do that. But I'm going to go ahead and lump these and call this 5D10. It actually goes after, so I'm going to drop that one off and just lump it with this one. If you put it in the front or the back, I don't care. There's a minor energy difference there. Okay, so then 5D10 gets us to Mercury, and then what's the last tail?
6p2.
6p2. Okay. Pew doggies. How many electrons is that?
82.
82. We shouldn't have to count if we know we tracked them as we went. Okay. So as a side note, take a breath. Okay, good news. How many times have we done this 1s2, 2s2, blah, blah, blah? Like a million times, okay? We keep repeating. Do you possibly think there's a shortcut? There's gotta be. Nobody has time to do this longhand. If I say longhand, I want longhand. If I say shorthand, you can do noble gas shortcut. Hence, you gotta know where the noble gases are. Where are they?
The last one.
Last one. So you take where we are, back that baby up to the last noble gas you passed. Xenon. Okay, what's xenon's electron configuration? Where does it stop up here? It goes from here to 5p6. Okay, so what I have in brackets, if I allow you to do shorthand, but if I say noble gas shortcut or something like that, you can do bracket, xenon, bracket, and that means this. Okay? So if I say noble gas shortcut, go for it, but don't mess up and go to the wrong noble gas. Now, noble gas shortcut doesn't finalize it though. XE bracket means that first bit, you'd still have to finish up with what?
the 6s2.
6s2.
4f.
Sorry, I got mixed up. 6s2, 4f14, 5d10, and 6p2. But it's much more manageable. So you have a lot of tools under your tool belt, but probably the favorite tool.
So what is all this called?
Electron configurations are the written out ones. Orbital diagrams are the up and down arrows. That's basically all we learned today was electron configurations and orbital diagrams. Kendall?
Okay, so why aren't you like doing all this electrons?
Because we have to know that where the electrons exist because it gives us information about their reactivity. The ones, that valence shell I told you about, those are the only ones that react. So it gives us information about the reactivity. Yes?
If we're trying to do shorthand for a noble gas, we do the noble gas beforehand and then all the electrons.
So, good question. And she said if she wants to do the noble gas shortcut for a noble gas, just bracket that noble gas. It's cheap, but it's okay. You can do longhand on noble gases. Question?
Okay, so like, let's say we have to do the actual, like, the diagram for it. We still do the bracket, or do we have to write everything out?
Generally, I'll say no, because that's not really accepted in the scientific world. But something like this, I feel your pain. So I'd rather you at least, you can bracket the first,
But then do like the
and then
last
do the
one.
last, because I need to see, how many valence electrons and so forth are there, or open spots and orbitals. Question?
For anions and cations, where do those electrons go?
So I'm gonna do as a warm up tomorrow, but note to self, cations do what with electrons? They lose electrons. So where's that sodium at? Sodium. Did I just move this?
Yeah.
Oh, thank you. Okay. So sodium's this blue one up here, right? Sodium's this blue one, right? Yes. How many valence electrons does it have?
3.
Whoa. Valence electrons, outside shell. 1. Guess what sodium does? Drops that thing off, and it becomes sodium 1 plus ion. That's where the ions come in.
Anions and cations deal with mostly valence electrons.
Only with valence electrons. If you touch the inner core, we're gonna have problems. Inner core electrons are everything on the inside. These are inner core. And ions will cause a change in valence electron count. Very, very good question. Yes, ma'am.
So before the 4F14
Yeah.
lead, you put 5D1, but then after the 4F, you put 5D10.
I put 5D9 initially. So then I took that 1 and the 9 and I clumped them together to make 10. Because it's stupid to put them in two separate places. They're the same orbital type.
So you wouldn't technically separate.
Yeah, you do it by chance because you're just following through our table. Think about it at the end and go, can I clump these? Yes, and then just do it. I won't take off either way. That's where it gets kind of fishy. I'm just happy we made it there. I'm happy we made it to F block, okay? So I'm usually pretty flexible unless it's just totally off in left field.
Are we doing a test?
Yes, thank you. All right, so let me pause on electron configurations. I appreciate that. So tomorrow I'm not going to see you, right, for intervention time. Thursday I'll see you for intervention. I'm going over parts of this test during intervention. We will do something I call them test corrections because you know what that means. But in honors chemistry, AP chemistry, I did not give credit back on tests because you did not adequately prepare. So instead I give you a free 100 quiz grade for your efforts, and I appreciate that. But I want you to start looking over these tonight for yourself. Problem set 5 will be finished tomorrow, yes?
Yes.
Okay, so come and grab these from me. The sheets are here. Constant, the blue number is your final score. Just Ethan's not here. Connor. Let's go, Connor, thank you. Joe. Natalie.
Were they relatively okay?
You guys left room for improvement. Josh. You guys left room for improvement. Elijah, Chris,
I think I got about 50 or 40.
Brandon.
Anything better than a 60, I'm happy.
Right. I'm going to talk to you guys about your expectations for yourself in a second. Andrew. Chris, come back.
I'm sorry.
Jonathan, Zach. I answered that in the 7-3 Megan. Kendall. Kendall, Max, so take a second to look and then let's chat. Oh, Kenya, I have yours, but I have your multiple choice. I still make Kenya sometimes. So I'll put back your mark, okay? Because I have your, I haven't scored your Scantron yet, so I can't tell you. To be honest, I can't tell you because I don't know. Alright, and I still have about 3 minutes left in class, so I need your full attention back to me, okay? So, as a notice for your review that you're going to be doing, I will be going over a couple of the dimensional analysis questions because many of you guys just didn't read the instructions and say dimensional analysis. That means fractions and using the units and kind of canceling them out. So I try to get back as many, like kind of keep you in the loop of show your work, I'll give you credit. The final answers were absolutely not right if you didn't show units and correct sig figs. So your final answer, if you messed up in the middle of a problem, I don't do double jeopardy. Like I don't count, oh, they got the conversion wrong and they got the answer wrong. I'm not going to double jeopardy you. I'm going to say conversion was wrong, answer's correct for your work, as long as you had correct sig figs and units. So me like repeating that over and over again, do you see now in the middle of the unit where I'm like, units, sig figs, looking back to give you some feedback. That's my goal, to kind of make sure that I support you as much as I can mid-unit. So, you know, I'm not saying what I think is important, but listen up, okay? So, in terms of the feedback, the green numbers, which like 31 over 38, there were 38 points available on the entire free response. So, there were a couple things that were just like sig fig missed, maybe you messed up. Some of you guys wrote your products and reactants really funky. So, products are on the, what side of the arrow? Right, and then the reactants on the left. Most of you guys did really fine with the rest of that. The measurement one on the back for sig figs, you have to use your estimated digit, just like we did in the lab with the ruler. It was estimate one further. So if you would like to save some time and start correcting this, you can. Correct meaning read, show some work, correct sig figs. If I do it in a different color pen, because eventually I'll take this back and I'll look for effort. If the effort's there, 100.
Attention students, from 82 is back in service.
Because you can just fix one thing and then recalculate. So it's fine. I'll give you back the multiple choice on the day that we take, the intervention day.
You get a 50 class? Chris, I'm sorry. What'd you get? How would you get? You know what?
Cancer. So, ready? Last thing, and I'll leave you alone. I know you guys are advanced, and I know that you guys want to do really well. When you say, I hope I got a 50, you're doing that because, and to be honest, you're doing that because you know that you feel okay if you didn't get what you initially know you're capable of. If you know you're capable of a 90, and you say, oh, I'll get a 50, you're saying that you're settling for something you're less than. And you know you can do more. And that was the first test. I expect you guys were probably a little bit like, oh gosh, I don't know the format, hold on. I'm expecting 80% averages. It was a 66 average for this class. 80% are higher than honors. Bye.
Yo, we're in the alley.
That's fantastic.
So I'm